Okay, so now we have some problems associated with Le Chatelier's principle. And to start off, we're asked to consider what happens to the position of equilibrium for these processes when the volume is reduced. Now, we know that from Boyle's law. What does Boyle's law tell us? Well, Boyle's law tells us that pressure is inversely proportional to volume. P is proportional to 1 over V. That's an inverse proportionality. So as volume increases, pressure will decrease. And so if volume is reduced, pressure will increase. So if we're looking at a reduction in the volume, that means there's going to be a pressure increase. Okay, now if pressure increases, according to Le Chatelier's principle, a system at equilibrium will try to re-establish equilibrium once a constraint is applied to it by opposing that constraint. And so if we increase the pressure, the system is going to try to re-establish equilibrium by reducing the pressure. And of course, if we have an equilibrium that involves gases, the only way that the equilibrium can respond is to change the number of molecules in the gas phase, because the pressure of the gas is a result of the collisions between gas molecules and the walls of the reaction vessel. So if the system needs to decrease the pressure in response to our increase in the pressure, the system will do that by reducing the number of molecules in the gas phase. Okay? So in order to understand how the equilibrium will shift, we need to look at the number of molecules in the gas phase on both the reactant and the product side. If we consider this first reaction, you can see that on the reactant side there are 6 molecules in the gas phase because P4 is a solid, and on the product side there are 4 molecules in the gas phase. So quite clearly there are more molecules in the gas phase on the reactant side than the product side. So if the system is trying to reduce the pressure, the equilibrium in this case will shift to the right, because in doing so the number of molecules in the gas phase will decrease, and that is what the system is trying to do. Okay, it's trying to counteract the increase in pressure that we are imposing upon the system. Likewise, if we look at the second reaction here and count the number of molecules in the gas phase, we have 2 molecules in total on the reactant side, and we have 1 molecule on the product side. So again, there are fewer molecules in the gas phase on the product side than there are on the reactant side, and so the shift again will be to the right hand side in order to reduce the number of molecules in the gas phase, thereby reducing the pressure. If we look at the final reaction that we have here, and again count the number of molecules in the gas phase, here we have 1 and 3, so that's a total of 4 molecules in the gas phase on the reactant side, and here we have 1 and 3, which is a total of 4 molecules on the product side. So quite clearly there are equal numbers of molecules in the reactants and the products, so there will be no shift, because it's not possible for the equilibrium to shift one way or the other in order to reduce the number of molecules in the gas phase. So the equilibrium simply can't respond in this case to try and establish a lowering of the pressure. Okay, so that's an example of how the equilibrium will respond to pressure changes. If we then consider how the equilibrium will respond to temperature changes, we have 2 examples here that we need to consider. Now, bear in mind again that Le Chatelier's principle says that when a constraint is applied to a system at equilibrium, the system will try to re-establish equilibrium by opposing the constraint that's been applied to it. And as you can see here, that the constraint that's applied is one of a temperature increase. So if we are imposing a temperature increase on the system will try to decrease the temperature, or it will oppose our increase in temperature by imposing or trying to impose a decrease in the temperature. And it can decrease the temperature by absorbing heat or moving in the direction that absorbs heat. And a process that absorbs heat is one that is endothermic. So if we increase the temperature, the system will try to decrease the temperature by absorbing heat. That is, the equilibrium will move in the endothermic direction. Okay. Now if we look at this first example here, you can see that we've got N2 reacting with O2 to produce 2NO in the gas phase, and the enthalpy change for this process is 181 kilojoules per mole, which is of course endothermic because it's a positive number. Okay, so bearing in mind that we're looking to favour the endothermic process once we increase the temperature, quite clearly then the system will move to re-establish equilibrium by moving to the right, because that is the endothermic process. And of course if it moves to the right, we're going to have more products than reactants, so that means that the equilibrium constant will increase in this case. If we look at the second reaction that we have down here, the enthalpy change for that process is minus 198, which means that the forward reaction is exothermic. And if the forward reaction is exothermic, the reverse reaction is endothermic. And that's the reaction that will be favoured, as we've already seen. So in this case, the reaction will move to the left. Whoops. Will move to the left, which will mean that Kc, the equilibrium constant for this, will decrease. Because if the reaction moves to the left, we're going to have higher concentrations of reactants, lower concentrations of products, which means that the equilibrium constant itself will decrease. Now, one final thing to consider then are the effect of concentration changes on the equilibrium. And it's useful when we consider concentrations just to consider the expression for the equilibrium constant. So if we write down the expression for the equilibrium constant for this chemical reaction that we have here, it's going to be the concentration of the product, ammonia squared, divided by the concentration of nitrogen, multiplied by the concentration of hydrogen raised to the power 3. And so if we were to add some nitrogen to this equilibrium reaction mixture, what would happen? Well, if we added more nitrogen, that means the concentration of nitrogen would increase, and so this ratio of concentrations would decrease below its Kc value. And if it drops, that means that the equilibrium has to shift to the right. In order to produce more product, decrease the concentration of N2 and re-establish this ratio of concentration so that it has its Kc value. If we were to add ammonia, what would happen to this ratio of concentrations? Well, if we add ammonia, the concentration of ammonia on the top here would increase, which means that the ratios would be above the Kc value. So in order to re-establish equilibrium, the concentration of ammonia would have to decrease and the concentration of nitrogen and hydrogen would have to increase. That would mean that the equilibrium would have to shift to the left towards the reactants. Okay, so we can always understand what happens to equilibrium when we change concentrations by thinking about how the affected concentration will cause the Kc value to change, and then how the equilibrium can re-establish in order to move the concentrations such that they attain their Kc ratio.